Across the satellite era, the band of tropical rain that helps organize winds over Africa has been drifting north. A new 2026 study built from observations and climate model experiments found evidence that the planet's zonal mean intertropical convergence zone has migrated northward since 1979. That sounds abstract until you put one of Earth's largest sources of airborne dust beside it. Saharan dust does not leave Africa on a fixed highway. Its route depends on where strong surface winds lift particles, how high those particles rise, where the rain belt sits, how the African easterly jet is arranged, and which pressure systems steer the air once the plume reaches the Atlantic or Mediterranean. Move those pieces even a little, and the same desert can send dust toward very different places. That is the shift worth watching. It is not a satellite image showing the Sahara suddenly sliding north. It is not proof that next month's plume will hit Florida instead of Spain. And it is not a forecast that one destination is about to stop receiving dust while another is about to get buried in it. The new signal is subtler and potentially more important. The atmospheric system that helps determine where tropical rainfall, trade winds, and dust-producing circulation line up is changing on a multi-decade scale. Stay with me, because the most surprising part is that a separate 2026 study points to a future dust shift that is not simply north follows north. Under strong greenhouse gas forcing, in that model, westward Saharan dust transport moved toward lower latitudes instead. That apparent contradiction is the story. If you watched the Sahara from space this year, you would already see why simple rules fail. In February, a broad Saharan plume spread across the eastern Atlantic, affecting the Canary Islands, Cabo Verde, and Madeira. In late March, a dust front roughly 2,000 kilometers long formed over southern Algeria and pushed south through Mali and Mauritania before reaching the Atlantic and the Canary Islands. In April, another plume emerged from Egypt and curved across more than 1,000 kilometers of the eastern Mediterranean. In May, satellite imagery caught dust moving east from Libya across the Mediterranean. Same desert, different source regions, different steering winds, different destinations. Those 2026 events are not evidence that the long-term rain belt shift caused any one storm. They are a reminder that Saharan dust is a transport problem before it is a destination problem. And the transport system is three-dimensional. The Sahara is the largest source of airborne mineral dust on Earth. Strong winds can lift particles from dry lake beds, loose sediments, and other exposed surfaces into the atmosphere. Once lofted, dust can remain suspended for days and sometimes much longer. Some plumes stay relatively low. Others enter the Saharan air layer, a hot, dry, dusty air mass that commonly extends several kilometers above the Atlantic. During the peak summer season, the Saharan air layer repeatedly moves westward from Africa. NOAA describes outbreaks forming every few days during the active period, with some reaching the Caribbean, Florida, Central America, and Texas. At other times of year or under different pressure patterns, major plumes can turn north toward Europe, northeast toward the Mediterranean, or southwest toward the tropical Atlantic. That seasonal wandering has been visible from satellites for decades. NASA imagery shows the core Atlantic dust band shifting north as the year advances. In winter, dust commonly tracks toward lower latitudes in South America. By summer, the transport corridor shifts north toward the Caribbean and the southeastern United States. So, dust routes already move. The question raised by the new research is whether the climate scale background on which that seasonal movement occurs is changing too. The first clue comes from the tropical rain belt. The Intertropical Convergence Zone, or ITCZ, is a relatively narrow region where trade winds meet and air rises, producing some of the planet's most persistent tropical rainfall. Its exact position changes with the seasons, the oceans, hemispheric temperature, contrasts, atmospheric aerosols, volcanic eruptions, and other forces. A small latitudinal shift can reorganize rainfall over enormous areas. That matters intensely in West Africa. The late 20th century Sahel drought is one of the clearest examples of how a displaced tropical rain belt can reshape lives, vegetation, surface moisture, and the atmospheric circulation around the southern Sahara. The new Geophysical Research Letters study examined the satellite era from 1979 through 2024. The researchers found evidence of a northward migration in the annual zonal mean ITCZ. Their analysis also showed a similar reversal in climate models when those models were driven by anthropogenic forcing. The study attributed important roles to declining northern hemisphere aerosol pollution and rising greenhouse gases, with a smaller contribution from major volcanic eruptions. The key word is reversal. During the latter half of the 20th century, the ITCZ had shifted southward in response to strong hemispheric forcing differences. Around the early 1980s, that trend stopped in the models. Since then, the satellite-era signal has gone the other direction. But calling this a Sahara shift without explanation would be misleading. The ITCZ is not the desert boundary. A northward moving tropical rain belt does not mean dunes physically march north. It does not mean vegetation instantly covers the Sahara. And the 2026 study is about the global zonal mean ITCZ with regional differences that matter greatly. Still, the Sahara sits next to one of the places where ITCZ movement has consequences that can reach far beyond rainfall. Because rain changes the land, wind changes the dust, and the atmosphere connects both to places thousands of miles away. There is another reason the timing is interesting. This new climate result arrived in the same year that satellites documented Saharan plumes traveling in several sharply different directions around North Africa. Those storms do not prove the trend, but they give the abstract circulation problem a visible shape. They show exactly why a changing background pattern matters. Dust has many exits from the desert. To see why the rain belt matters, picture the southern edge of the Sahara at the start of the West African wet season. North of it, the desert surface is intensely hot and dry. South of it, monsoon moisture pushes inland from the Atlantic. Between them lies the Sahel, a transition zone where rainfall can transform bare or dormant ground into grass and vegetation in a matter of weeks. Satellites have watched that seasonal green-up for decades. NASA vegetation records show the belt of plant growth moving north with the rains and retreating when the rains move south. That changing surface matters because exposed dry soil is easier to mobilize than wet or vegetated ground. But moisture is only one part of the dust machine. You still need wind strong enough to break particles loose and lift them. You need atmospheric turbulence or convective processes to carry them upward. And you need a steering flow that keeps them suspended and moves them away from the source. That is why more rain does not translate into a simple map where dust disappears wherever the ITCZ moves. A classic NASA-supported line of research connected warmer North Atlantic conditions, a more northerly tropical rain belt, weaker trade winds over African dust source regions, and reduced dust transport across the Atlantic. In that framework, a warmer northern Atlantic weakens the winds that pick up and carry dust while also allowing tropical rainfall to reach farther north, damping some source regions and increasing vegetation. That mechanism is real enough to matter, but it is not the only mechanism in the system. A dust storm can be triggered by a cold pool outflow from thunderstorms. Strong synoptic pressure gradients can drive enormous fronts. African easterly waves can help organize cyclonic circulation that lifts and transports dust. The African easterly jet can change the level and direction of transport. Mountain gaps, dry basins, surface roughness, soil moisture, and prior rainfall all influence where the next plume begins. That is why the satellite record often looks like a moving puzzle. On March 30 this year, Copernicus Sentinel-2 saw a giant dust front cross the Algeria-Mali border. The front was not drifting lazily west from a single source. It was a wall of airborne mineral particles driven by strong winds moving southward through West Africa before reaching the Atlantic. The event disrupted trans-Saharan transport routes and contributed to a severe Kalima episode in the Canary Islands. A few weeks later, Sentinel-3 saw a very different path. Dust originating from Egypt arced over the eastern Mediterranean. The plume stretched more than 1,000 kilometers over water, thinning from dense brown near the source to diffuse filaments farther away. Then in May, Meteosat-1-2 captured dust heading east from Libya across the Mediterranean. If you only looked at one of those events, you might assume the direction was the trend. It was not. Each storm was a snapshot of weather riding on top of climate. The long-term signal is not dust now goes east or dust now goes south. The long-term signal is that some of the background controls on rainfall, surface conditions, and circulation are evolving. That can change probabilities and preferred pathways without dictating the route of the next individual plume. This is where the second 2026 study becomes important. Published in Geophysical Research Letters in April, it asked what increasing greenhouse gas forcing could do to westward Saharan dust transport from West Africa. The researchers used the WRF atmospheric model with a dust module and compared a historical simulation with several future forcing scenarios. Their most important result was not simply more dust or less dust. It was a latitudinal redistribution. Under the high-emission simulations, the model shifted more of the westward transport toward the equator compared with the historical period. The strongest changes appeared at lower latitudes between roughly 4 and 15 degrees north. In the model, the increase in westward dust transport within that low-latitude band was about 34% in one low-emission late-century experiment, about 54% in a high-emission mid-century experiment, and about 96% in the high-emission late-century experiment relative to the historical model baseline. Those numbers are dramatic, but they need a boundary around them. They are modeled future changes, not observed 2026 dust increases. The model also underrepresented total present-day westward dust transport compared with observations. That means the percentages are best understood as changes within the model framework, not literal forecasts for how many extra tons of dust will cross the Atlantic in a specific future year. The study's authors emphasized that the shift in latitude may matter more than the change in total transport. That idea is the key to the title. Where dust goes can be as important as how much dust exists. Move the transport corridor south and the plume interacts with different parts of the tropical Atlantic. Move it north, and the Caribbean Gulf or southeastern United States may see a different frequency of exposure. Send more dust toward the Mediterranean, and southern Europe faces different air quality and aviation impacts. But here is the twist. The new ITCZ study found a northward shift in the tropical rain belt, while the new dust model study found an equatorward shift in future westward transport under strong forcing. That does not mean one study cancels the other. They are asking different questions. One detects a multi-decade change in the global rain belt using observations and climate models. The other isolates future Saharan dust transport in a regional atmospheric model under different forcing scenarios. The dust response is not controlled by latitude alone. It is controlled by the whole circulation. This also explains why a greener Sahel does not simply shut off the Sahara. The main source regions are spread across an enormous landscape, and a wet anomaly in one zone can coexist with exposed sediments and strong winds somewhere else. A climate shift can therefore redistribute dust production instead of switching it off, changing both the timing and the latitude of export. That whole circulation is why the Sahara can send one plume toward Texas and another toward Greece. The desert provides the particles. The atmosphere chooses the route. In summer, the Saharan air layer often rides west above the cooler, moister marine boundary layer. This elevated structure helps dust survive the Atlantic crossing. The warm, dry air can reduce cloud growth and interact with tropical waves, while the dust itself absorbs and scatters sunlight and changes heating within the atmosphere. The plume is therefore not passive cargo. Dust can modify the environment carrying it. That is one reason researchers care about shifts in its latitude. During hurricane season, the overlap between dry, dusty air, tropical waves, sea surface temperatures, and wind shear can influence whether disturbances struggle or organize. A dust plume does not automatically kill a hurricane, and the 2026 modeling study does not predict future storm counts. But changing where the dry, dusty layer sits changes which developing systems encounter it. The Caribbean and southeastern United States have another reason to care: air quality. Saharan dust commonly stays elevated, but some particles mix toward the surface. When concentrations rise, particulate matter can aggravate respiratory conditions and reduce visibility. The health effect depends on how much dust reaches breathing level, not simply whether a satellite sees a plume overhead. South America has a very different relationship with the same mineral particles. NASA's Calypso measurements showed that Saharan dust can cross the Atlantic and deliver nutrient-rich material to the Amazon basin. Phosphorus carried from North African soils helps replace some of the nutrients lost from the rainforest through heavy rainfall and runoff. The Atlantic Ocean receives nutrients too. So a transport shift is not just a meteorological curiosity, it changes where minerals, particles, dry air, and radiative effects are delivered. And that is why satellites are central to this story. Dust is too large a system to understand from ground stations alone. A surface monitor can tell you how much particulate matter is in the air at one city. It cannot show the full plume stretching from the Sahara to the middle of the Atlantic. A rain gauge in the Sahel can record a storm. It cannot map the global position of the tropical rain belt. Satellites fill those gaps. Passive imagers, such as MODIS and VIIRS, can map the horizontal spread of dust and vegetation. Geostationary satellites, such as Meteosat and GOES, can watch plumes evolve hour by hour. Dust RGB products combine infrared channels to make airborne dust stand out from clouds and desert surfaces, including at night. LiDAR adds the vertical dimension. NASA's Calypso mission used pulses of laser light to reveal where dust sits in the atmosphere and distinguish mineral particles from other aerosols. That vertical information matters because a plume at 5 kilometers behaves differently from dust trapped near the surface. Climate researchers then combine those observations with reanalyses, sea surface temperature records, precipitation estimates, and models. This is how a shift that would be almost impossible to see from the ground becomes measurable. But the phrase satellites caught a major shift still needs one more correction. The satellites did not capture a single moment when the ITCZ jumped north. The shift emerges statistically from decades of observations. That difference matters, because climate signals do not behave like breaking news events. There is no frame from one morning that shows the old rain belt on the left and the new one on the right. Researchers compare long records, define the location of tropical rainfall, smooth short-term noise test trends, and then ask whether models reproduce the change under known forcing. The 2026 ITCZ study used exactly that kind of approach. Its strongest claim is that a growing observational record reveals a northward migration of the zonal mean ITCZ over the satellite era, and that anthropogenic forcing can reproduce that reversal in models better than internal variability alone. It does not say every longitude moved north by the same amount. It does not say every region of the Sahara is becoming wetter. It does not say Saharan dust will now take one new permanent route. And it definitely does not say the next plume can be predicted from the long-term trend. Those are all bigger claims than the evidence supports. What the evidence does support is a changing background state, and that background can alter the odds. A separate 2026 Mediterranean study shows another way to think about this. Researchers built a Saharan dust flux and transport index from 22 years of data combining surface particulate matter, satellite-derived dust, optical depth, free tropospheric dust, mass transport conditions, and large-scale climate indices. When they examined how dust transport related to the North Atlantic Oscillation and El Niño, the relationships were neither fixed nor uniform. The NAO connection was stronger than the ENSO connection across several Mediterranean subregions, but it changed through time and from place to place. Western and eastern parts of the Mediterranean showed more persistent coupling than the central Mediterranean. That result reinforces the same message. There is no one master switch for Saharan dust. Not the ITCZ, not the NAO, not El Niño, not greenhouse gases, not vegetation. The route emerges from several controls interacting at once. So when a model shows a future equatorward shift that is not a contradiction of a northward moving global rain belt, it is a warning against turning one climate indicator into a dust forecast. The Sahara responds through a network of winds, moisture, surface changes, and atmospheric waves. And the network can rearrange itself in ways that are not intuitive. For air quality forecasting, that distinction is crucial. A plume routed a few degrees farther south or north may encounter different islands, shipping corridors, population centers, and weather systems before it settles. The atmosphere does not need to produce more dust overall for the consequences to change. It only needs to deliver a different fraction of the plume to a different receptor region. That brings us to the question behind the title, where does the dust go next? For the next individual plume, the answer is weather. Forecasters look at current source regions, surface winds, pressure systems, tropical waves, the African easterly jet, the Saharan air layer, and downstream steering. Satellite imagery shows what has already been lifted. Aerosol models then estimate where that dust is likely to move over the following days. In mid-August, this is especially relevant because the Saharan air layer is still in its climatological peak season. NOAA notes that activity typically ramps up in June, peaks from late June into mid-August, and produces new outbreaks every 3 to 5 days during active periods. That means a long-term climate shift does not replace short-term forecasting. It sits underneath it. The next plume can still go north while the long-term Atlantic transport tendency shifts south. A year can produce major dust over Europe, even if the multi-decadal Atlantic total declines. A wet Sahel can suppress some dust sources, while a powerful storm activates another dry basin farther north. Climate changes the background probabilities. Weather chooses the day. The 2026 dust storms make that obvious. The February plume spread across the eastern Atlantic. The March event drove a massive front south and west. The April plume curved from Egypt over the eastern Mediterranean. The May event moved east from Libya. In July goes, 1/9 continued to monitor dust across the tropical Atlantic and Caribbean. None of those paths is the new permanent normal. They are examples of what the atmosphere can already do. The deeper question is whether the frequency of those routes, the height of the plumes, the preferred source regions, and the amount of material carried along each corridor will change as the background circulation evolves. That is where the science is headed. One branch of research is trying to improve dust detection itself. Satellite instruments can struggle to separate thin dust from cloud smoke or the bright desert surface. Multi-channel infrared products help, and newer geostationary imagers provide much more frequent observations than older systems. Another branch is trying to improve source representation. Not every square mile of Sahara produces dust equally. Dry lake beds and fine sediment deposits can be disproportionately important. Soil moisture can shut down a source temporarily. Vegetation can stabilize the surface. Rainfall from a previous week can matter as much as the wind on the day of the storm. A third branch focuses on transport. How high does the dust rise? Does it enter the Saharan air layer? Does convection lift it above a plateau? Does a tropical wave carry it west? Does a Mediterranean cyclone pull it north? Does the plume stay elevated over the Caribbean or mix? Down into the air. People breathe. The 2026 studies add one more scale to that stacked climate. The rain belt itself has shifted. Future dust transport may shift too. But the direction is not a one-line answer. That uncertainty is not a weakness in the story, it is the point. The original title says, "Satellites caught a major shift in the Sahara." The more accurate version is that satellite-era records reveal a major shift in Earth's tropical rain belt, one of the atmospheric systems that helps shape conditions around the Sahara and Sahel. The original title says that shift could change where the dust goes next. That part survives with a condition. It could change the long-term distribution and preferred pathways of Saharan dust. It cannot tell us the route of the next individual plume by itself. The April 2026 modeling study shows why the pathway question deserves attention. Under strong, forcing its future westward dust, maximum moves toward lower latitudes with more transport south of about 15 degrees north and less at some higher latitudes. The authors argue that the latitude shift may matter more than the total amount. If that pattern emerged in the real climate, it could change which sections of the tropical Atlantic experience the strongest dusty air, how often dust overlaps with tropical disturbances, and where downstream ecosystems receive material. But that is a scenario from a model. It is not an observed 21st century migration of the dust corridor yet. At the same time, older NASA-supported research points toward reduced total African dust transport as the North Atlantic warms relative to the South Atlantic trade winds weaken and the tropical rain belt reaches farther north. Those two ideas can coexist. Less total dust does not mean the same geographic distribution. A shrinking plume can move. A corridor can narrow and shift. One latitude band can lose dust while another gains it. That is exactly why future dust cannot be described with a single number. There are also feedbacks. Dust reflects and absorbs radiation, interacts with clouds and ocean ecosystems, and can alter the thermal structure of the atmosphere. Change rainfall and vegetation, and you change the surface that produces dust. Change hemispheric temperature contrasts, and you change the circulation that helps position the rain belt. That does not mean scientists can predict a dramatic tipping point in Saharan dust. No such threshold is established by the 2026 studies. What they can do is watch the pieces. They can track the latitude of tropical rainfall. They can measure Atlantic temperature contrasts. They can map vegetation and soil moisture across the Sahel. They can monitor dust optical depth over Africa and the oceans. They can use LiDAR and models to estimate the vertical structure of plumes. And they can compare where the strongest transport occurs from year to year. For viewers in the Caribbean, Florida, Texas, Southern Europe, or the Mediterranean, the practical meaning is simple. The Sahara is not a remote background feature. It is part of an atmospheric system that connects continents. Dust lifted from one basin can dim skies thousands of miles away. It can irritate lungs in an island city, feed nutrients to an ocean, fertilize distant ecosystems, and alter the environment around tropical weather systems. The next plume will still be controlled by the next pattern of winds, but the stage those winds operate on is changing. And that is what the satellites are beginning to reveal. Not a desert suddenly moving, not a new dust highway appearing overnight. A slow shift in the planet's rain belt, a set of models pointing to changing dust pathways, and a growing satellite record showing how sensitive those pathways already are. The final image to keep in mind is not a dune. It is the boundary visible from space between brown dust and bright tropical clouds. That boundary moves every season. Now scientists are asking whether the map beneath that seasonal motion is moving too.